A 10-liter vessel contains gas at a temperature of 0 degrees Celsius and a pressure of 4 atmosphere. How many moles of gas are in the vessel? How many molecules are there? We are looking for the number of moles of gas in the vessel. Obviously, you need to go back to the ideal gas law. What do we know here? We know the volume is 10 liters at a temperature of 0 degrees Celsius. The temperature is 273 Kelvin. Pressure is 4 atmosphere. Now remember, we got the volume in liters, pressure in atmospheres. Therefore, the value of R will be R equal to 0.08206 liter atmosphere per mole per Kelvin. Always remember to use the right value of R depending on the units of volume and pressure. So we got the volume, temperature, pressure, and the value of R. We can now obtain the value of N. PV equal to nRT is the ideal gas law. We have all these values except N. Therefore, N equal to PV divided by RT. That will be 4 atmosphere times 10 liters over 0.08206 liter atmosphere per mole per Kelvin times 273 Kelvin. And look at the units now. You can see liter and liter, atmosphere and atmosphere will cancel. Per Kelvin and Kelvin will cancel. And per mole will go up. The unit, when you simplify it, will be mole. N equal to whatever number you get, that many moles. So that will be 1.79 moles is the number of moles of that gas in that container. Okay? How many molecules are there? If you know the number of moles, what do you do to find the number of molecules? Multiply that with the Avogadro number, the number of molecules in a mole. So the number of molecules in 1 mole is the Avogadro number, 6.03 times 10 to the 3 molecules. Therefore, the total number of molecules will be the number of moles multiplied by the number of molecules per mole. That will be 1.79 times Na. That will be 1.79 times 6.03 times 10 to the 23. That is 1.08 times 10 to the 24 molecules. Okay, let's do another one. A room is 6 meter by 5 meter by 3 meter. That means you can find the volume in meter cube. If air pressure in the room is 1 atmosphere and the temperature is 300 Kelvin, find the number of moles of air in the room. You can do that the same way we did in the previous case. If the temperature now rises by 5 Kelvin and the pressure remains a constant, how many moles of air leave the room? Alright, let's first find A by writing down the given values. First of all, pressure is 1 atmosphere. Temperature is 300 Kelvin. R is 0.08206 liter atmosphere per mole per Kelvin. Volume of air is, the room is 6 meter times 5 meter. How do you find the volume of the air in a room? Length multiplied by width multiplied by height. So the volume of air in the room is 6 meter times 5 meter times 3 meter. That is 90 meter cube. There's a problem here. If you want to use pressure in atmosphere, then the volume must be in liters. If the volume is 90 meter cube, how many liters are there? In order to convert meter cube to liters, 1 meter cube contains 1,000 liters. So multiply this by 1,000. You get 9 times 10 to the 4 liters. Now once you have all these values, N equal to PV over RT. So put in all these values as before, and we get the number of moles is 3,656 moles. You got so many moles of air in the room at that temperature. Now what is happening? The temperature rises by 5 Kelvin. Now you know that in the room the volume is going to remain a constant. Is that right? Alright. Now in B, when the temperature rises by 5 Kelvin, the final temperature is 305 Kelvin. So the new number of moles of gas in the room now will be N equal to PV over RT. Now pressure remains the same. We are told that the pressure remains a constant and the volume also remains a constant. Is that right? When the temperature increases, will the room change its volume? No. The room is made to a fixed volume. So the volume remains a constant, which is this. So that will be pressure multiplied by volume, and this is R, and this is temperature. The only thing that changes is the temperature. Now, that gives me 3,596 moles are contained in the room now. What was the original value? The original value was 3,000, I don't remember. The number of moles of air leaving the room is, the original value was this, 3,656, minus, now what is remaining is 3,596. So 60 moles of air has left the room. Alright? Another example. A container with a volume of 6 liters holds 10 grams of liquid helium. As the container warms to room temperature of 20 degrees Celsius, what is the pressure exerted by the gas on its walls? Well, let's pick the given data. The volume of the container is 6 liters. And we have 10 grams of liquid helium. Well, mass is 10 grams. The temperature is 293 Kelvin, 20 degrees Celsius. 20 plus 273 is 293 Kelvin. R is 0.08206 liter atmosphere per mole Kelvin. As the container warms to room temperature, what is the pressure exerted by the gas on its wall? Since the molecular weight, do you know the molecular weight of helium? If you look at the periodic table, it gives you the atomic weight. The molecular weight of helium is 4. That means 1 mole of helium has a mass of 4 grams. Now, if you don't know that, now try and make a note of this. The molecular weight of a substance in grams is numerically equal to the weight of, well, the molecular weight of helium is 4 grams, means 1 mole of helium has a mass 4 grams. If the molecular weight of water is, 32, that means 1 mole of water has a mass of 32 grams. Alright? So the molecular weight of helium is 4, means the mass of 1 mole of helium is 4 grams. and we have 10 grams of helium. How many moles of helium do we have? Each mole of helium has a mass of 4 grams. Therefore, 10 grams of helium contains 10 divided by 4, which is 2.5 moles. So therefore, 10 grams of helium contains 2.5 moles. Okay, so N equal to 2.5 moles. Now we have PV equal to nRT. We got V, we've got N, we've got R, we've got T. We can find the pressure. What is the pressure exerted by the gas on its wall? Pressure equal to nRT divided by V, and use all the given values. That gives you 10.12 atmosphere. Why is the pressure measured in atmosphere? Because we use the value of K in liter atmosphere per mole per Kelvin. So the calculated pressure will be in atmospheres. But you must be able to do any such problems using the gas laws and the ideal gas law.